So everyone can hear me, right?
Yes.
Excellent, thank you. So, and if the audio ever cuts out, just put something in the chat or let me know so I don't keep blasting through. So let's call this curve r of t. And what is the unit tangent vector? So if we parameterize the curve so that as t increases, so as t increases, we move this way along the curve, then the unit tangent at some point is just the direction that the curve is going at this point, all right? And I think one of the best examples to illustrate unit tangent vectors is the spiral, okay? So let's do an example that sort of meshes with physics a lot. And I think you did something similar in class, but I still think it's a good example to talk about. So you can parameterize this curve by cosine theta, sine theta. Okay, I like to think of this curve as, you know, when you go to the airport and you go to the parking garage and you want to park on the 6th floor and you have to go up a big ramp. This is sort of how I think about this curve. And so let's say that we have a car that's moving up this ramp. And this is the equation of motion for the car. So the car is at position r of t, r of theta at time theta, all right? And so if we want to find the velocity of this car, then all we have to do is we take the derivative of this guy with respect to theta, all right? And that just means that you're taking the derivative in each slot. And that gives you minus sine theta, cosine theta, 1. Okay, and let's see when you project this down onto a circle. So let's say that we take the spiral and we just flatten it. So if we project it down onto a plane, it just becomes a circle. All right, hopefully everyone believes that. And what the unit tangent vector is, it gives you this direction along the circle. Okay, and now in physics, you might remember, if you ever took a calculus-based physics course, that you start out with position, r of theta, you take a derivative, and you get momentum, or velocity, sorry. And if you take a second derivative, you get acceleration, right? So let's compute the acceleration here. The acceleration is given by, so it's just another derivative, so minus cosine theta, minus sine theta, and 0, okay? And one of the things that might have been drilled into you when you took high school physics was that when you're moving in a circle, you have this mysterious force called the centripetal force, which is pulling you inward, okay? And the centripetal force is two things. It's perpendicular to the direction of the momentum, and it is in the direction of the acceleration, okay, towards the center of the circle. And so let's check that in this case, even in the 3-dimensional case, we still have a centripetal force that's perpendicular to the direction of motion. So what do? We just take a dot product, r prime theta, with r double prime theta, okay? And that gives you sine theta, cosine theta, minus cosine theta, sine theta, plus 0, okay? And these cancel, and that just gives you 0. So does this make sense to everyone? How about F's in the chat if it makes sense, or C's if it doesn't? Great, I see some F's. Cool. So hopefully this isn't too redundant for you. There's one other concept that I think is extremely important and maybe doesn't make total intuitive sense, which I'll try and illustrate for you. So this concept is the idea of curvature, okay? The first few times I saw curvature, it didn't make much sense to me. And actually, I don't think I intuitively understood why the curvature is what it is until yesterday when I reviewed this to teach it. And then it made more intuitive sense. I knew how to compute it, of course, but why this gives you the curvature, probably this is a little bit murky to you as well, right? So let me try and make some sense of it for you. The equation for the curvature is given by r prime crossed with r double prime. And then you take the magnitude and you divide by r prime cubed. Okay. And so what does it mean for a curve to be curved? Okay. Well, you have a line and you know that the line is not curved, right? And why is the line not curved if you're just traveling along the line? Well, the reason is because let's think about so think about it in terms of velocity and acceleration, okay? If you're traveling along the line, your velocity and your acceleration only have two directions to go in. And those are forward and backwards, okay? And if you take the cross product of two things that lie on a line, then you're going to get zero, right? And so then you get zero curvature up here. But in which case, what is the most curved two-dimensional curve that anyone can think of? Does anyone have any ideas why I charged my Apple Pencil? So what is the most curved two-dimensional curve that you can possibly think of? Yeah, nice. Thanks, Olivia. It is a circle. And let me explain why that is. So if you have a circle and you're moving around your circle, then we already said that the velocity and the acceleration are going to be perpendicular to each other, okay? And I think one way to rationalize what is curvature, for a curve at least, is when you're moving along the curve, the more that the acceleration points in a perpendicular direction to the velocity, the more curved it is, because that's closer to a circle, all right? And one way to think about this mathematically, like why is this mathematical? When you take this product, remember that the resulting magnitude is the area of the parallelepiped by the way, okay? So when is this the greatest? Well, if you have a parallelepiped that's very angular like this, this is going to have a smaller area than if it's a square. Area is going to be maximized if this is a square or a rectangle. And what does it mean? A rectangle. It really means that the velocity and the acceleration are pointing in perpendicular directions. Okay, so that's going to maximize this expression up here, thereby max curvature. Okay, so hopefully this is somewhat enlightening as to why this is the right expression for curvature. Any questions? Questions? Very well. Don't be shy, but we're going to go on to the worksheet since no one has any questions. Okay, so let's start by doing problem one. I think problem one is a little bit of a review from last week, okay? But it's still a good review to do. So let's work out problem number one and put F's or C's in the chat if you understand or are confused, respectively. And at any point, if you have any questions, feel free to let me know. And if you're confused and embarrassed, of course, there's no reason to be embarrassed, but regardless, you can just private message me or C. Great, we have one F. Three Fs, great. Happy to see that. Also, if you're waiting for other people, I would be very interested to hear if you could DM me, what did you think of our midterm? Did you think it was hard, easy, doable? Did you think that the review that we did prepared you adequately? Be interested to know. Great, thanks to everyone who responded. Okay, I think we have enough Fs that we should go over it. So our curve is given by R of t equal, and if we want the tangent line to this curve at the point 1, 1, 1, the first thing that we have to do is figure out for which t at 1, 1, 1. Okay, so all we have to do is set t squared, t cubed equal to 1, 1, 1. And this is the same as setting t equals 1. All right. And so that means that our starting point is going to just be 1, 1, 1, of course. And our derivative is given by taking the derivative of this thing, which gives you 1, 2t, and 3t squared. And then all we have to do is plug in t equals 1, and we get plus 1, 2, and 3, okay? And then we have to parameterize. So because we already used t, let's just throw an s in there, all right? So hopefully that makes sense to everyone. Let's go on and do problem 2. I think problem 2 shouldn't be hopefully too much of a stretch after this one. Oh, so I have a question, which is why did we use nestigate? The reason is because we want a parameterization for the line, right? And in order to get a parameterization, we have to have some sort of variable to parameterize by. And I just chose this one because we already used t to parameterize the original curve. And so I didn't want people to get confused between traveling along the curve and t and thinking that, oh, okay, we can just plug in the same value to this equation, because it's not the case. So I used a different variable. Yeah, sure. Okay, we're getting some Fs, I'm happy. But I'd also be happy to see any Cs. Okay, I have one C, so if you're, it's a private chat C, so yes, F. Okay, F is, I guess you could think it stands for finished, but I actually got it from F's in the chat, like F to pay respects, even though I don't play video games. I went to a math camp where everyone else did, and they always put F's in the chat. And C is indeed for confused. But I didn't think of that. Yeah, I guess F could stand for finished as well. Yeah, I don't really keep up with my memes very well. Has it gone out of fashion? Is there something new that people? No, I don't play games at all. I don't play games at all. Do you play games? Do people in this chat play? Okay. All right, so I think I have enough Fs in the chat to keep going, and one C, which is good too. So our curve is T e to the T minus at the 0, 0. Okay, so as before, the first thing we have to do is just figure out this. And the way we do that is we set this vector equal to this point, okay? And obviously, if you just look in the first coordinate, you get it has to be equal to 0. And now we want the speed of the parameterization, right? And what do? We take, first we have to find the velocity because magnitude of velocity is equal to speed. And that gives you 1 minus 9t, okay? And now we have to plug in t equals 0, which gives you 1, 0, 1, all right? So that's a vector. And now we just have to take the magnitude of this, okay? And that gives you 1 squared plus 0 squared plus 1 squared square root, and that's equal to root 2. Okay, so hopefully that's what everyone else got. Okay, let's go on to problem 3. Only very baby games. I don't know what a baby video game is. To me, that means like the Wii. I also think when people are working, I might have that I'll go. This is kind of annoying. I think it's legally necessary. Okay. So first we want to find the length of C, right? And let's talk about what it means to find the length again. So in order to find the length of a curve, we somehow, well, okay, the first problem is if we're going around in a non-straight line, there's not an obvious way to say what the length of that is, okay? And so the only thing that we can reasonably do is we can break it up into little lines. Because if we have little lines, we know how to find the length of each line and we can add them up and it's a close approximation to the length of the curve. And then all we have to do is just shrink these lines down until they're infinitesimally small. And this is the same thing as finding the differential velocity of this curve and then integrating, integrating that differential velocity, okay? Or sorry, I mean speed, because that's the distance that we're going to travel, okay? And so how do we do this? First, we have to find the velocity. So r prime of t is equal to 2, 6 cosine 3t, and minus 6 sine 3t, okay? And now we have to take the magnitude. So squaring each component, we get 4 plus 36 cosine squared 3t plus 36 sine squared 3t. And then we, of course, take a square root. And that gives you, so we have a cosine squared and a sine squared. So we get 4 plus 36 root. And so that gives you root 40. So now that we've found the differential velocity and speed, all we have to do is integrate this guy. So root 40, let's integrate by s so that no one gets confused. So we'll integrate by s. Oh no, sorry. Let's integrate by t, because this time we are actually moving along the curve. So we'll integrate by t, and we're just going from 0 to 2 pi, okay? So, sorry, that should be a dt. And that gives you 40 square root t from 2 pi to 0. That gives you 2 pi root 40. Okay, any complaints? Is everyone happy with this? I'm trying to find Zoom again. Okay, is everyone happy? Is this what you got? Can I scroll? Yeah, sure. Great. Okay, so let me kind of blast you through the next couple parts because I think they don't really deserve to be separate questions by themselves. And at any point you can tell me to scroll up and you can take a screenshot or something if I'm going too quickly. Okay, so what is the arc length function here? So the arc length function usually is denoted by s of t. I don't know why. I don't know what it stands for. So s of t is just root 40t in this case, because as we move forward in time t, we have this amount of arc length by what we did previously. And so when they ask for an arc length parameterization of t, what they're asking us to do is just take the total arc length, and then we want 0 to be the start of the curve and 1 to be the end of the arc length, okay? And so in this case, what we're doing is we're just going to replace t. So we want to rewrite t in terms of the arc length. So we have s of t over root 40 is equal to t, okay? And now we just have to plug this guy in to our original equation, or at least I think this is what they're going for. So what does that look like? It should be 2. So remember, our original curve was 2t, 2 sine 3t, and cosine 2 cosine 3t. Okay? Yeah. And so plugging this back in gives us 2. I'm not going to write s of t, so I'll just write s. So s over 40, 2 sine 3s over root 40, and 2 cosine 3s over root 40. And that should be, I think, your arc length parameterization. So is everyone happy with that? Awesome. Let's let's go on. So I don't think there's nothing conceptual here about curvature, but I think it's still good to have to compute the curvature once. Let's compute the curvature in problem 5. Okay. I'm going to go over this now because I need at least 3 minutes to do this, and I only have 2.5 minutes. So let me go over it. And if you're not done, just do these computations in the privacy of your own home, because they're really rote calculations. So let me compute this for you. So we have r of t, and it's equal to 3 minus e to the t minus 4 and 8t minus t squared. Okay. And we need to find the velocity and the acceleration at t equals 4. So is going to be minus 4 and 8 minus 2t. And we plug in 4 and that minus 1, 1, and 0. For the acceleration, we have to differentiate the velocity a second time, and we get 0 e to the t minus 4 and minus 2. Plug in 4 and get 0, 1, minus 2. Okay, another thing, the other two quantities that we're going to need are we need the magnitude of r prime t. So that's just minus 1 squared plus 1 squared plus 0 squared root. It's equal to root 2. And we need the cross product. So that's minus 1, 1, 0, and 0, 1, minus 2, I hat, j hat, k hat. We take the determinant, that gives us minus 2, minus 0, minus 2, minus 0, and then, sorry, I'll have to write the coordinate down here, and minus 1, minus 0, okay? And so that's equal to minus 2, minus 2, minus 1. Okay, so let's take the magnitude of this. That gives us 2 squared plus 2 squared plus 1 root, and we divide by root 2 cubed, okay? And that's going to give you, so 2 squared and 2 squared, that's 8, plus 1 is 9. So root 9 over root 2 cubed. And so that's just 3 over 2 to the 3 over 2, okay? And hopefully if you put an F in the chat, that's what you got to. Otherwise I made a computational mistake probably. So any input? Okay, so no one has anything to say, I guess. People agree with me, or? Okay. Great. Okay, so people who put F's in the chat, well, I guess they didn't say anything, but other people agree with me, so I'll have to assume that's right. If you didn't get it or were too slow, please go back, make sure you know this formula, make sure you can compute it. Otherwise, you could get in trouble on the next exam. And you won't know how to compute curvature in your daily life. So, okay, that's it for this week. Thank you so much for coming to section. And I hope I'll see you next week. And feel free to stick around if you have any questions.